we will have one more exercise on cardinality. In this exercise, we will see that the cardinality of R, the set of all real numbers, is exactly the same as the cardinality of a very small subset of R. And this we can actually compare with one of our previous problems in which we observed that the cardinality of the set of all integers and the cardinality of a proper subset of that, which is a set of all natural numbers, they are exactly the same. We are going to the problem. This is the question that we are going to see now. We have to show here that minus 1, 1 and the set of all real numbers have the same cardinality. And to establish that the cardinalities are the same, we have to make use of the function fx equal to x by x square minus 1 from minus 1, 1 to set of all real numbers. So we have to verify that this function is 1, 1 and onto from minus 1, 1 to r. So if we look at the graph of this function, we can get some idea about why we specifically choose this function. The graph of the function looks like this. So this is the graph of the function fx equal to x by x square minus 1 in the range minus 1, 1. So suppose that we mark minus 1 and 1 here. This is minus 1 here, the left endpoint of the interval, and 1 here. And we can see that the graph of the function stays somewhat flat near to 0 and becomes rapidly increases when it moves towards minus 1 and towards plus 1. So this y-axis we can consider to be the set of all real numbers, and we can see that corresponding to any real number. Of course, this is extending. This graph is extending towards. This is extending upwards. This is extending. This is extending in this direction, extending upwards and extending downwards. So we can see that this graph is also extending. So this will be going again, going further upward this way, and this will be going downward in this way. This is not going to touch this line through minus 1, line through plus 1. This is not at all going to touch. So we can see that corresponding to any real number, suppose that we choose a real number that is on this y-axis. So corresponding to any real number, we can find a point on this graph. So this is actually, this graph is going to give, if you take all the y values on this graph, you will be getting the complete r. We'll be getting the complete r. So we are going to make use of this function to show that minus 1, 1 and r have the same cardinality. And note that one more thing, this is onto because of this reason, that whatever r we choose corresponding to r, we can find a point on this graph, and corresponding to that point we can find an x here. So this is some c corresponding to c. This is some c corresponding to c. We located this point, and corresponding to this point we have this point here. So this function is going to be onto in that sense. But what about 1, 1? So we can see that, suppose that from the very look itself, it appears that this function is 1, 1, because if two elements have not for different x's, they cannot definitely have the same y as the image. So from the graph, it looks that this function is going to be 1, 1 and don't do, but we have to prove it using algebraic methods. That's what we are going to do now. We are going to prove that fx equal to x by x square minus 1 is 1, 1 and onto. So to show that this function is 1, 1, we will suppose that f of x is equal to f of y, and we will try to see if x is going to be equal to y. So we'll show that's 1, 1 first. Let f of x equal to f of y, and our aim is to show that we have to show that x equal to y. This is what we want. So f of x equal to f of y, by the definition, this is x by x square minus 1 equal to y by y square minus 1. If we just rearrange the terms, we get x into y square minus 1 equal to y into x square minus 1, and therefore xy square minus x is equal to yx square minus 1. So if we further rearrange, xy square minus yx square equal to, sorry, here it is y, x minus y, and if we again do some manipulation, we have xy into y minus x is equal to x minus y. This is what we are getting. So xy, if we bring this x minus y also to the left side, we have xy, this is nothing but equal to minus of y minus x. So xy into, sorry, this is, okay, this is correct. So xy into y minus x plus y minus x is equal to 0. Therefore, y minus x into xy plus 1 equal to 0. If y is not equal to x, what will happen? If y not equal to x, then y minus x is non-zero, but the product is 0. Therefore, xy plus 1 must be 0. Then xy plus 1 equal to 0. And xy plus 1 equal to 0 means that xy equal to minus 1. So this is the observation we have. If y is not equal to x, we will be having xy equal to minus 1. But remember that x and y are both numbers in the domain of the function, which is minus 1, 1. So x belongs to xy belongs to minus 1, 1. And therefore, modulus of x is less than 1 because it is between minus 1 and 1. Modulus of y is also less than 1. So modulus of xy is less than 1. Modulus of xy must be less than 1. But here we are getting, this implies that modulus of xy is equal to 1. So these two things cannot go together. This is a contradiction. This is a contradiction. And so what we assume must be wrong. And so x must be equal to y. Therefore, x must be equal to y. Therefore, we started with fx equal to fy and we got x equal to y. That is, fx equal to fy implies that x equal to y, or f is 1, 1. So we established that this function is 1, 1. To show that this function f is onto corresponding to one c on this real line, we have to find a point here in such a way that that c is equal to f of x for some x in minus 1, 1. So now we are going to show that this function is onto. Next is f is onto. This is what we are going to verify. So we choose one c in R. Our aim is to find, we have to find x in the interval minus 1, 1 such that f of x is equal to c. Okay, f of x equal to c means that we have to find x such that x by x square minus 1 equal to c. So c is given and we have to find x. So this means that x is equal to c x square minus c, or further manipulations we get c x square minus x minus c equal to 0. So this is what finally we are getting. Cx square minus x minus c is equal to 0. So can we find x satisfying this? That's the first question. After that, we can think if that x is going to be in minus 1 or minus 1 to 1. First question is, can we find some real number x satisfying this? So for that, we are going to make use of the discriminant quadratic equation concepts. And if we look at the discriminant of this is a quadratic equation, and of course this is not a quadratic equation if c is equal to 0. So if c is equal to 0, what will happen? If c equal to 0, then x by x square minus 1 equal to 0 implies that x is going to be equal to 0. There is no other way. So if c is equal to 0, we already have x, and that x is in, this belongs to minus 1, 1, and we don't have to look for any other x. So we can safely assume that c is non-zero. So we assume Suppose C is not equal to 0. Now we are going to look at discriminant. Discriminant of equation 1, this is equal to b square, which is minus 1 square minus 4 into minus c into c. This is 1 plus 4 c square, and this is definitely greater than 0 because for c square it's always non-negative, 1 is positive, therefore this is greater than 0. Therefore one equation 1 has two distinct solutions. So we get that equation 1 has two distinct solutions. And in fact, C not equal to 0 is not really necessary here because if C is equal to 0, what will happen is this is just equal to 1 and the discriminant is, okay, still there is a confusion. Okay, we will assume C not equal to 0. That's necessary here. So one has two distinct solutions. And now the question is, at least one of the solution must belong to minus 1, 1, so that we can say that the function is onto. So if you consider the two solutions, what are the two solutions? So let the solutions be, the first solution is x1. This is equal to the quadratic equation formula, 1 plus root of 1 plus 4c square discriminant by 2c, and x2 equal to 1 minus root of 1 plus 4c square by 2c. Since we have already assumed that this c is not equal to 0, this is not going to create any problem for us. So we safely assume that c not equal to 0. Okay. Now remember that x1, x2 is going to be, no, we will verify that. So if we try to look at this x1 and x2, what is the product? x1, x2 is nothing but 1 minus 1 plus 4c square by 4c square, that is equal to a minus 4c square by 4c square, that is minus 1. Therefore x1, x2 is minus 1. This is an important thing. We are going to make use of this. Okay, now we are going to have two cases. We will see if c greater than 0 what happens, because if c greater than 0, in the graph we have seen that if z is on this side, this part above the x-axis, that the corresponding x must be lying in minus 1, 0. And if c is on c is below the x-axis, then the corresponding x is going to lie in 0, 1. So we have actually two cases. C is equal to 0, we have already seen. C is equal to 0, x is also 0. If C positive, what happens? C negative, what happens? That is what we are going to see now. So if C is positive, okay, then we already have x1 equal to 1 plus root of 1 plus 4c square by 2c. Remember that c is positive. Therefore, 1 plus 4c square, if we replace by just 4c square, is greater than 1 plus root 4c square. If we simply remove 1, this is all positive. Therefore, this is equal to 1 plus 2c by 2c, which is 1 by 2c plus 1. And 1 by 2c plus 1, because 1 by 2c is positive, c being positive, this is definitely greater than 1. So x1 is greater than 1 if c is greater than 0. That is one observation. But we know that modulus of x1, x2 equal to 1, because x1, x2 is equal to minus 1. Modulus of x1, x2 equal to 1. Therefore, modulus of x1 into modulus of x2 equal to 1. But modulus of x1, we have already seen x1 is greater than 1. Therefore, this is greater than 1. So to balance, x2 is 1 by mod x2 is 1 by mod x1. Mod x2 is 1 by mod x1, and therefore this is going to be less than 1. Therefore x2 must lie, mod x2 is less than 1 means that x2 must be between -1 and 1. So we got the solution to be x2, and x1 is going to be outside -1, 1 because its modulus is greater than 1. So if c is greater than 0, we have a solution in -1, 1 for f of x equal to c. So f of x2 will be equal to c. Now we are going to the second case. In the second case, we are going to assume that c is less than 0. If we assume c less than 0, we can probably guess that instead of taking x1, we have to probably take x2. x2 is equal to 1 minus root of 1 plus 4c square by 2c. Remember that c is less than 0. Therefore, if we just take 1 plus 4c square here, this is minus. So numerator will become something more, but we are dividing with a negative. Therefore, the total quantity will become something less. The total quantity will become something less. See, numerator 1 plus 4c square, instead of that, suppose we take 1 minus root of 4c square. So numerator we are increasing because we are subtracting something less. Numerator we are increasing, but we are dividing with a negative quantity. Therefore, the total quantity will be decreasing. Therefore, it is this. This is equal to 1 minus 2c by 2c, which is equal to 1 by 2c minus 1, or this is equal to minus 1 plus 1 by 2c, and this is a negative quantity. This is a negative quantity, and minus 1 and a negative quantity. Therefore, this is going to be something less than minus 1 because it's going to be something lying to the left of minus 1. We are adding again a negative quantity to minus 1. Therefore, x2 is less than minus 1. Therefore, mod x2 must be greater than 1. And again, mod x1, x2 equal to 1, mod x1, mod x2 equal to 1. This is greater than 1. Therefore, mod x1 must be less than 1, or x1 must be in the interval -1, 1. Therefore, f of x1 equal to c is the solution. x1 is the solution in -1, 1. So in either case, we get f of x2 equal to c or f of x1 equal to c. Therefore, c has a pre-image x1 or x2. Therefore, f is onto. So we established that f is 1, 1 and f is onto. Therefore, -1, 1 has the same cardinality as r. This is quite surprising because -1, 1 is really a small subset of r. It's very small in the sense that r is an infinite interval, -1, 1 is somewhat a very small interval, but still their cardinalities are the same. So the cardinality, even though in the beginning we hope that the cardinality will give us some feel of comparing to sets, just like we compare to real numbers, doesn't really look like so, because since we have a huge set going to have the same cardinality as that of a much smaller set.